This project developed a smart indoor comfort monitoring system using Arduino Uno. It is to monitor temperature, humidity, and light intensity. The system automatically controls lighting, fan, and indicators to maintain a comfortable indoor environment while providing manual override and safety features. So the problem statement is the indoor comfort is often controlled manually. It leads to inconsistent environment. It is no real-time monitoring of temperature, humidity, and light. So the users may forget to turn on or off lights and also adjust ventilation. So to existing system lag, we need an automation and also safety features. But the sensor failure may go undetected. So we need a system that monitors environment continuously, respond automatically, provide manual control, override, and also ensure safety and reliability.
The smart indoor comfort monitoring system uses an Arduino Uno as the main control and power board, and this system can operate in both automatic and manual mode. In automatic, the system uses a TMP36 sensor to measure temperature, while potentiometer measures humidity input. Based on these readings, the system determines 3 comfort zones of hot, cool, or comfortable, each indicated by a different LED. The fan is controlled at different speeds or off, depending on these conditions. The system uses an LDR sensor to detect surrounding light conditions, such as when the environment is dark and light system switches on. When it's bright, the light switch off. In manual mode, the users can control the lighting system manually and push the push button to switch freely between auto and manual modes. For monitoring and feedback, the system uses both an LCD display and serial monitor, and these outputs show real-time information of humidity, temperature, light condition, and the current operating mode.
Okay, first, the system starts by initializing all components like sensor, LCD, and Arduino. It then reads temperature, humidity, and light data and converts them into usable values. Next, the system checks the temperature condition to control LEDs and the motor based on whether it is cool, comfortable, or hot. After that, it checks the light intensity to determine whether the environment is dark or bright. The system also validates sensor readings. If there is an error, a red LED will blink as a warning. If there is no error, the system reads the push button to toggle between manual and automatic mode. In manual mode, the user controls the light using a switch. In automatic mode, the system controls the light based on the light sensor value. Finally, all data is displayed on the LCD and printed to the serial monitor, so the process repeats continuously in a loop. After that, we end.
At the start of the system switching on, it is first set to be in the automatic mode. In the comfortable zone of temperature between 19 to 30 degrees and humidity between 30% to 50%, the green LED switches on and the fan runs at low speed. Both conditions must be met simultaneously. When the temperature is lowered, the cool zone is entered and the yellow LED switches on. The fan switches off. When the temperature is raised, the hot zone is entered and the red LED switches on and the fan runs at high speed. Temperature is set to be the first condition to check. However, if the temperature is set to be comfortable range, but the humidity is below 30%, the system reads it as entering the cool zone. Hence, the fan switches off and the yellow LED switches on. If the humidity raises 50%, although still temperature is in comfortable range, the system reads it as entering the hot zone. Hence, the fan switches on at full speed and the red LED switches on. The lighting system depends on the LDR sensor. When it is bright outside, the lighting system will switch back off. When the LDR senses it is dark outside, the lighting system will switch on. The user can toggle between the auto and the manual mode. To enter the manual mode, the button is pressed. Hence, the lighting system can be controlled by the user by pressing the push button again. The system will re-enter automatic mode.
Now, I'm going to talk about the breakdown of the coding. Student 1 is responsible for sensor integration for temperature and humidity. The code is created to read the analog temperature and convert it into degrees Celsius. And then, the temperature is categorized based on the threshold values. Lastly, the system reads the humidity. For this part, these are the variables used in the temperature and humidity system. They store sensor readings such as temperature value, humidity output, and converted Celsius value for further processing. In the setup function, the temperature sensor is connected to pin A1 and the humidity sensor is connected to pin A2. In the loop function, we create code to convert analog temperature into degrees Celsius. The equation for conversion is shown here. Then we print the temperature with the calculated value. Also, we need to read the humidity and convert into percentage humidity. The equation for the conversion is shown here. Similar to temperature, we print the calculated humidity percentage. Lastly, for student 1, we set up threshold values to categorize the temperature range using an if-else statement. If the temperature is less than 19 degrees Celsius, the status is cold. If the temperature is in between 19 degrees Celsius and 30 degrees Celsius, the status is comfortable. If the temperature is more than 30 degrees Celsius, the status is hot.
Okay, so next for the sensor integrations for the light intensity. So for this task, we build a system that detects the ambient light and automatically controls an LED. During the day, it stays off, and at night, it switches on. The sensor reads a value between 0 to 1023 from the analog pin, and we set 500 as our threshold. Below 500 means it's dark enough to turn the LED on, but 500 and above means it's bright enough to let it off. So here are the four variables we declare. The sensor is wired to analog pin A0 and the LED is on digital pin 9. We also store the live sensor reading in light value and keep the threshold at 500. In the setup function, we configure A0 as an input and pin 9 as an output, then print a message to the serial monitor so we know the program started correctly. And every loop cycle does two things. First, it leads the current sensor value using an analog read and prints it to the serial monitor so we can see it live. Then it checks the threshold. If the value below 500, it writes high to the LED pin during it on and prints night equal to LED on. Otherwise, it writes low, turning the LED off, and prints day equals LED off. And that's full automation. No manual switching needed. Thank you.
Now, for Student 3, this part is a continuation of Student 1. Student 3 integrates the actuator control system, which is the comfort response system. There are three conditions: comfortable, green LED on and fan at low speed; cool, yellow LED on and fan is off; and then hot, red LED on and the fan at high speed. So these are the variables and setup function for the actuator system. The pins for the LEDs and the fan are defined and configured as outputs. Next, we set up the conditions for the three different zones, which are hot, cool, and comfortable. This is done using an if-else statement. Firstly, when the temperature is more than 30 degrees Celsius, or when the temperature is between 19 and 30 degrees Celsius, but the humidity is more than 50%, it is considered hot zone. Therefore, the red LED is turned on and the fan runs at the highest speed. For the cool zone, it is when the temperature is less than 19 degrees Celsius or when the temperature is between 19 and 30 degrees Celsius, but the humidity is less than 30%. In this condition, the yellow LED is turned on and the fan is turned off. Lastly, for the comfortable zone, when the temperature is between 19 and 30 degrees Celsius and the humidity is between 30 and 50%, the green LED is turned on and the fan runs at low speed.
Okay, now let's go through to the fourth part of the coding, which is manual override and safety features. In the code, several variables are declared. Button pin and switch pin define the hardware inputs for the push button and slide switch. Manual override and manual light are boolean flags that track whether the system is in auto or manual mode. Last button state, store the previous button reading so the code can detect a press event. Error flags like time error, light error, and humidity error check accessibility and system error will combine them. And finally, last blink and red state are used to control the blinking cycle of the red LED. And next, we're going to the void setup. In the setup function, the push button and slide switch are configured as inputs with pull-out resistors. This ensures stable reading and prevent faulty values. By preparing these pins, the system can reliably detect button presses and switch positions. Okay, now we're going to the first part of the loop, which is check sensor readings. If temperature, humidity, or light value fall outside valid range, the system error equals to true. For example, in this example, temperature error, if it below -10, it will be system error will be equals to 2. It will be equals to true. This acts as a safety gate before normal operation continues. And then for the safety fallback, the second box, when system error is true, the red LED begins to blink every 400 milliseconds. This is achieved using the Millis function, which allow non-blocking timing. At the same time, the serial monitor prints a warning message, which is shown warning, sensor failure detected. So this ensures the user is immediately aware of a failure or assumed conditions. Okay, now we are going to the third part of the void loop section of the student 4. So push button logic. The push button is used to switch between auto and manual mode. This purpose is to allow the user to decide whether the LED should be controlled automatically by the sensor or manually by the switch. The code detects a transition from high to low, meaning the button was pressed a short debounce delay of 15 milliseconds will prevent fast toggle. Each press flips the mode and brings the change to the serial monitor. And illusion, switch to manual mode or switch to auto mode. And next, the last one, slide switch and light control. This one we combine it together. The slide switch defines how the LED behaves depending on the mode. So the purpose is to give direct control in manual mode while still allowing automation in auto mode. In manual mode, the LED responds directly to the switch position. In auto mode, the LED responds to ambient light via the LDR threshold. This ensures the system respects user preference while still offering automation when desired.
look at how they set up in the code. So under the variables, we initialize the LCD using the liquid crystals dash 12C, setting the 12C address to 0 time 27 with 16 columns and 2 rows. And in both setups, we first start serial communications at 9600 baud rate for the serial monitor, and for the LCD specifically, we run wire dot begin to start the 12C communication, initialize the LCD, turn on the backlight, and clear the screen. Then we display the system starting message for 2 seconds before clearing it, giving the user a clean startup confirmation. Inside the void loop, this is where the real-time display happens continuously. In line 1 of the LCD shows the current temperatures and humidity formatted as something like T equal to 28 degrees Celsius, and H is 65%. And in line 2 shows the light status and mode, where the logic works like this, where if the manual override is active, it checks the LED pin. If it's high, it prints light, otherwise dark. And if the automatic mode, uh, it checks the light sensor's value against the threshold, which printing dark if below the threshold or light if above. And it also shows whether the systems is in manual or auto mode, so the user always knows who's in control, the sensor or themselves. Yes, that's all. Thank you.
So based on our project on smart indoor config system, we get to conclude that the system has been successfully developed, where the Arduino system it get to monitor temperature, humidity, and light in real time. Not only that, the objectives has been achieved, where it get to detect conditions and respond using LEDs, fans, and lighting. Therefore, the automation and manual control has also been worked, where it works automatically, but it allows user override for a certain flexibility. Not only that, at the end of the thing, it has a real-time monitoring, where the data has been displayed on LCD and serial monitor, where it shows where the temperature is high or low, or the light has been dark or night, and even the mode of the toggle has been auto or manual.